Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 Chemistry students. Welcome back. How are you? I'm very fine and happy to be with you again. We are heading in for lesson 2 on our topic of chemical kinetics and the unit 13, which is basically about factors that affect the rates of a chemical reaction. As I had already said, we are coming in for lesson 2, and that is basically factors affecting the rate of the reaction, part 2. I'm calling it part 2 because we looked at one of the factors in our lesson 1. So I want you to distinguish it. So we're still continuing, but in this case, I'm calling it part 2. A quick review of what we looked at in lesson 1. We highlighted mainly on the collision theory and how it relates to the rates of chemical reaction. And we said the rate at which a reaction proceeds is actually proportional to the frequency of effective collisions. Of course, that is for reactants. What do we mean? The particles, atoms, ions, whichever you would want to call them, those are for reactants, must come together, must collide with each other with effective activation energy, or which I can say with enough activation energy, and so they produce the product. So in that way, we ended by saying any factor, any condition that would increase the collisions and increase the energies for the reacting molecules in the way that they can attain enough activation energy, then those factors will have an effect on the rate of a reaction. And in most cases, they increase the rate of reaction. But at the same time, we have some factors which actually slow down the rate of a reaction, as we shall see as we look through the factors, and that is specifically on the catalyst part. So, and we concluded the lesson by looking at those factors which we said: concentration of reactants, pressure for the case of gases, the surface area exposed for a reaction to occur, and the rest of these factors, as you can see. Then we only looked at concentration and said when you increase the concentration of the reacting particles, you reduce the distance between them, and so the end product is there will be high collisions, and with the high probability of colliding with each other, then high probability of having effective collisions, and so the reaction rate will increase. And that is for concentration as we looked at. So that is it, basing on what we looked at. And I left you with the exercise, which I believe you attempted. We shall come back on that later on. Now let's go to lesson content for our lesson 2. Still on the factors, but termed as part 2 because, as you notice, there are some factors we did not look at. So those are the factors we are going up to. In this lesson, much of the focus will be on how pressure affects gaseous reactants, what happens if you increase or decrease the temperature of a reaction. Suppose you add a catalyst in a chemical reaction, what happens to the rate? And if you have, for instance, a whole solid and you break it into different small bits, how will the reaction change? Or suppose you have small bits and you bring them together to form a loop, how will the reaction rate change? So these are the factors we shall dwell on mainly, and this takes us to our objective. I stated it to be one objective, but if you look through, you'll notice there will be almost like 5 objectives, because if you're to describe and explain each factor separately, then those will be almost 5 objectives. But the issue is you should be able to describe and explain how each of those factors listed alters or affects the rate of a reaction. If you can do that with illustrations and giving examples, you will have understood the lesson. So, let's go to factor 2, which is the pressure. Well, someone may wonder, you looked at concentration, why would you bring in pressure? Even because concentration can even apply to gaseous reactants. So one thing you need to notice is concentration encompasses all, but because for gases, the aspect is much more prominent when it is related to their pressure or to the pressure that they exert or the pressure that you exert. Unlike solids and liquids, which occupy a fixed volume, indicating if at all you compress, if at all you apply pressure, the pressure effect on them will be negligible. For gases, any slight change on the pressure or any slight change on the volume they are containing due to pressure change, then it will affect how they behave. So that's why for gaseous reactions, we base much more on the pressure. So let's see how it actually affects the reaction. Look at the slide, how it really affects the reaction. Suppose you have your container, look at it, with some gas molecules. You can see how spaced they are. You can see their direction of movement. Now apply pressure on the lid. When you apply pressure, the volume will reduce. Check note on the volume occupied. As the volume reduces, the movement of the gas molecules will be closer to each other. So the molecules will collide with each other so strongly than when there is limited pressure. So as such, any external pressure exerted on a gaseous reactant increases the rate of a reaction because the volume they are occupied in will reduce. As the volume reduces, the gas molecules will come closer to each other. As they come closer to each other, then there are high chances of having effective collisions. And so the reaction increases. So that is pressure relative to gas reactants. Again, concentration encompasses all of them, because when we talk of concentration, we're looking at the exact number of molecules of each reacting species. So, temperature. At least we all have an idea of temperature. So when temperature increases, the rate of reaction increases. When the temperature reduces, then the rate of reaction reduces. Let me bring you an example here. Most of us have always heard that after eating at night, you're not supposed to shower. Or the best way is take a shower, rest up a bit, then eat, rest up a bit, then you sleep. Indicating after eating and you directly go to the shower, you are decreasing the body temperature. And decreasing the body temperature, what will cause? The digestion will slow down because the body temperature is lower. Let me also bring in this other aspect. after eating, you're supposed to remain a bit active before you sleep. I think those are the behavioral changes that we normally go through. You're supposed to wait a bit before you go to sleep, and in that way remain active so as the body temperature can rise up. As it rises up, then the digestion is activated and the food you've eaten is digested. So this is a quick application on the aspect of the temperature on the rate. Before we come to the lab, or before we come to the reactions in the lab, can we look at ourselves? How does this temperature affect in any reactions in our body? As I've told you, after eating, the best is not to go to the shower room because you're taking a shower using cold water, which will lower the body temperature, and so the food will take longer to be digested. So when it comes to chemistry, any 10 degrees Celsius increase in temperature, it doubles the rate of a reaction. What does that mean? The rate of reaction increases greatly when the temperature also increases. The reason behind is simple. Temperature actually affects the rate of reaction in two categories. Remember what we said about collisions? To be effective, there should be enough activation energy. So what temperature does is it increases the kinetic energy. This kinetic energy brings about two aspects. With increase in kinetic energy, that means molecules will move very faster, and so the collisions will be high, in the sense that effective collisions are likely to arise. And in that way, the rate of reaction will increase. At the same time, this kinetic energy increases the activation energy. And so these colliding molecules are having enough energy for them to form the product. So that is how the temperature. So the first point to look at is look at the kinetic energy. Because when you increase the temperature, you increase the kinetic energy, which makes molecules move faster and attaining enough activation energy, so the reaction will be very faster. Let's take example of this curve. I will illustrate it again with the youth. Look at the curve. Let me use the youthful stage in a human development to illustrate this. You know, normally people of around 20, let me take it to 35, they are energetic, they are strong. So if I take that group of people and also form three categories of those people. One, the sick, in between 25 to 35, no, 20 to 35, you can have sick people in that group. Then you also have they are not sick, they are normal, but they are not muscular, they are not energetic because maybe they don't go to gym to mug up and be strong. So they are not strong. I will take them to be the intermediate. Then we have this other group. For them, they go to gym, they mug up, they've built their body, they are muscular, they are giants. So in that way, we have those three groups. The sick, yes, they are the youth, but they are sick, indicating they don't have enough energy. Then the intermediate, they are not sick, but they are not giants, they are not mugged up, and the mugged up and the giant ones. So if you take up that group, I would relate it to this curve. You have the number of particles, which I've told you the group, a group of 20 years to 35 maybe, then the energies in here. At the start, we are having few particles which are of low energy, the sick ones. Maybe there are few just sick, they don't have enough strength because of sickness. Then we have the majority who are not mugged up and not sick, the intermediate. This is where we have particles with the moderate energy in here. Then we have this other side, the mugged up and the giant. Some particles, they have high energy in here. So with our three categories of particles relative to our age group in the youth, remember? Then it gives us this curve when you increase temperature. I will still connect it up with our youth group. So suppose this middle part, these which are not sick and not energetic, you give them, you avail enough conditions, or you, for instance, you sponsor them to go to the gym and avail all the food requirements for them to develop up that muscle. They will also go to gym, mug up, and develop the muscle and become giants. So they will move from this side where they were in the middle, the moderate energy, to becoming the giants. So indicating the number of the giants will increase up. So this is what happens when you increase temperature. As you increase temperature, the molecules attain that more of the kinetic energy, so they will move from this middle part where they had moderate energy to the side where they have high energy. So with that taking place, they will attain the activation energy which is needed for a reaction to occur. You see the analogy now. With our middle guys, not energetic, and not sick, so all they're lacking possibly is the time to go to gym. You avail time, or it is the money to pay for gym, you avail the money. So in that way, they go to the gym and they mug up. So the number of mugged up will increase. In the same way, temperature in this case of reaction is what I would relate to the time for gymming, money for gymming. So as soon as the temperature is available, then the molecules will have higher kinetic energy, and in the process they will collide up with enough energy, which we call activation energy, and they will form the product. So basically that is how temperature affects the rate of a reaction. Let's look at factor 4, which is the surface area. This is normally applicable in solids. What you need to know is in any reaction involving a solid, the reaction takes place at the surface of the solid, indicating only those molecules at the surface will be the one taking part in the reaction. Take a close look at our slide. Take a close look at our slide. So you have particles which are exposed are those onto the surface. The particles in between or inside the solid do not take part in the reaction because they are not exposed. This is even applicable in simple understanding. Let me give you an example. Suppose two cars are colliding face to face. So when they are colliding face to face, the most affected part will be the face side or the front side, which is involving in the collision. So with that, the other back side, the behind side, will not be highly affected. And that is what happens with the reaction involving solids. So the inner particles are not involved in the reaction, only the surface is the one which is involved in the reaction. So now the question is, what happens if you break it down? What happens? Any thought? Directly, if you break it down, then you're increasing the surface area exposed for a reaction. Look at our illustration in here. The solid, which we call it a lump, has been broken down into different smaller bits. You notice that the inner molecules can now be free to react. So with the smaller surface area as a result of breaking down that solid part, then you increase the rate of reaction. Let's take a few examples in here. Calcium carbonate reacts with hydrochloric acid to form carbon dioxide and calcium chloride. It is actually a fast reaction. You see the illustration, the bubbling of carbon dioxide gas. So, if we use the green particles to be for calcium salt and the red particles to be for hydrogen ions, what do you notice? The reaction will take place at the surface. You see these red surrounding the green. The inner part remains, the particles are not taking part in the reaction. So in this case, the outer surface has to react first, the layer removed, then you go to the next and so on. So the reaction slows down. But if you break it down in this way, take a close look. Almost everywhere we are having a hydrogen ion and particles of the salt, calcium carbonate. So in this way, the reaction becomes faster. And actually, that is what we normally do. Normally, in any reaction involving the salt, you crush the salt to become powder or sometimes to become small crystals. Then the reaction becomes faster. That is for the surface area. Let's now look at one more crucial part, the catalyst. Well, when we were still in secondary, some students used to act as catalysts. Ask me how they used to act as catalysts. They would, if a student is saying, "Stop disturbing me, I will beat you," they would come and say, "Hey, you beat him and we see, beat him and we see." So in that case, they are acting as catalysts. And that is never a good thing. I'm even telling you, you students who are looking at me, please, do not always engage in such a kind of a behavior to catalyze for someone to be beaten or someone to be abused. That is no good. So when we talk of a catalyst, and I believe you've always said it, you're catalyzing. So when we talk of a catalyst, we mean in chemistry, we mean that substance which alters the rate of a chemical reaction but remains chemically unchanged at the end. Still coming back to our example of students saying, "You beat him. If you two guys fight, it's you and this other guy who is fighting with you that will sustain injuries. These other guys who are saying, beat him, they will not sustain any injury. Actually, they will go like the way they were." So you see the analogy in here. So in the chemistry, that catalyst, it alters. It can decrease or increase, as you're going to see, the rate of a chemical reaction, but remains unchanged. So it is there to catalyze, as you normally say. Look at the illustration given in there. You're having it at the start, the same structure at the end, the same makeup at the end. So that is basically a catalyst. So what you need to notice is there are two categories of catalysts. So we can have a positive catalyst and a negative catalyst. A positive catalyst, as you can hear the word positive, for it increases the rate of a reaction, and the negative, it slows down the rate of a reaction. I wish sometimes you students could always act as negative catalysts when a strike is to happen, or if someone is to beat another person and you say, "No, do not beat that person. Let's resolve things amicably." So in that way, you would be acting as a negative catalyst, but not saying, beat him, which would be in the case of a positive catalyst. So let's bring it back to chemistry. A positive catalyst, how does it exactly increase the rate of a reaction? So it increases the rate of reaction by simply lowering the activation energy in a way that it provides an alternative pathway. What do we mean? Remember, for a reaction to occur, must outweigh this barrier, the activation energy, which is the minimum amount of energy the reacting species must have for them to turn from reactants to products. So that barrier, if you reduce that barrier, if it was like 10 kilojoules and you reduce to 2 kilojoules, 2 kilojoules is easily attainable. So when that barrier is reduced, then the reaction can easily occur. And how does it reduce it? By providing a different pathway. Look at this example. Look at this example. You see, here we are having hydrogen peroxide and a bromide in presence of hydrogen. So in the usual way, uncatalyzed, you would have this way, the activation energy. But when you bring in a catalyst, the activation energy reduces, and so it easily forms a product. So that is how positive catalysts work. Some crucial terms we use in catalysts, which you need to know, are homogeneous catalysts and heterogeneous. Homogeneous, that's where the catalyst and the reactants are in the same physical state. Heterogeneous, they are in different physical states. An example is solid nickel. It is a catalyst for hydrogenation of alkenes. That is in producing margarine. You see the margarine. We all eat broband or the margarine. So this is the illustration of what happens. So nickel provides the surface area where these gaseous molecules get adsorbed. Nickel is a solid. The reactants are all gases. And you see how the reaction is occurring. So finally, we look at the effect of light intensity. And that is it. You see how it is exactly happening. Thank you for being part of the lesson. I'm glad to interact with you. Stay safe, and bye.